right, so we're going to talk about next generation base rollups today. There are some base rollups that are next generation. There are some base rollups that are last generation. You guys just learned about some. I'm going to tell you more about how you can become a next generation base rollup, kind of what the definition is, and then a little bit more about how I see the future of base rollups evolving. Cool, so this first section, we're just going to go through some of the traditional base rollup research, talk about the base rollups that have been explored in the past, some of the designs that have been proposed, and then we're going to understand some of their flaws, some of their weaknesses. So one of the very first designs that is used by Tyco today on mainnets is total anarchy base sequencing. This is like kind of letter of the law, exactly what Justin Drake proposed in last year, right? And it's very simple, very basic, right? It's called total anarchy because it uses a election system that is permissionless and allows anyone, that's the anarchy bit, to propose a block. So one key point here is that the sequencer is not elected beforehand. You don't know who the sequencer will be beforehand. You might know the Ethereum proposer because you can look at the Ethereum lookahead. We know 32 in advance. But the sequencer of the base rollup might not be the proposer. In Tyco's case, it is Tyco Labs for the majority of blocks. One other thing to note is that layer 2 block proposing is completely permissionless, right? There's no permissions involved. The way that this ends up playing out in practice is that we have this diagram up here. We have a bunch of sequencers, proposers in Tyco's system that give their blocks to the builder, to the MEV-boost builder, that would be Titan, Wintermute, etc. And they would take these blocks, order them in the layer 1 block, so each block proposal is a layer 1 transaction, and then send this completed block to the proposer through a relay and through the MEV-boost auction, right? And then eventually the proposer would propose this to Ethereum once they selected the block with the highest bid. So it's up to the proposer and the builder to choose which block created by these layer 2 sequencers or proposers actually gets onto the chain. Now, one design that aims to solve a few of the problems of the previous design is vanilla-based sequencing. So LimeChain, George Spasov put out this excellent bit of research that explained how we can actually solve a few of the foundational problems with total anarchy-based sequencing, right, the Tyco model. So the first kind of thing that we try with vanilla-based sequencing is a simple sequencer election, right? That gives us the ability to choose a sequencer based on some rule. We have a primary rule, and then we have a fallback as well. So the fallback in vanilla-based sequencing case is just total anarchy. So there's still some total anarchy here. And the primary sequencing is based on some election mechanism that is not clearly defined and kind of left to implementation in the initial research. So the other thing that vanilla-based sequencing includes is kind of very basic primitive support for delegation, which is allowing the Ethereum proposer to give the rights to their base rollup block to an external builder without directly going through MEV-boost. It's like external to the MEV-boost auction. Vanilla-based sequencing also included basic support for preconfirmations, which gives the, we heard about it last talk, but it gives the proposer the ability to promise things about the block that they will eventually propose. It does require some sort of delegation or some increased hardware constraints on the proposer. And so the design for preconfirmations has kind of wide-reaching implications for centralization vectors, for stake, and also for preconfirmations in real time. Now, the other thing that vanilla-based sequencing introduced that really caught my eye was revenue generation from a % of congestion fees. And you'll hear Justin Drake talk about this all the time. You'll hear me talk about this. Base rollups can capture revenue from congestion trivially, right? These base fees, if you're doing EIP 1559 EVM, right? They are represented on chain and are kind of understandable from within the EVM, within the state transition function. So you can view things about the fees. You can take these and you can do things with them, right? You can direct them to a treasury. You could give some of them to the proposer, or you could return them back to users. So kind of the problems with these that are actually really big problems, like Tyco on mainnet live is extremely inefficient. All forks of Tyco without major changes will continue to be extremely inefficient. One other problem with kind of total anarchy and vanilla-based sequencing is that there's kind of no built-in composability. Any composability is on a layer above the sequencing. And that's really unfortunate because whenever you have to build kind of another layer, you introduce complexity and centralization vectors of some sort. In the case of base rollups, that's quite possibly around preconfirmations, which means we could have centralized Ethereum stake, which we will want to avoid. The other thing is MEV revenue. So lots of people still have this misconception that base rollups leak MEV revenue, and that's true for traditional base rollups because they do not use an auction of any sort to kind of get an oracle into MEV. So if we look into layer 1 MEV research, we'll see things like execution tickets and execution auctions that are all designed to get some oracle price, essentially, of the MEV in a block. Now, the other thing to note about base rollups, like I mentioned before, is inefficiency. So Tyco has about a $10,000 a day cost to do their sequencing. Before blobs, they had about $100,000 a day. This is a lot of money, clearly, and the kind of thing that you need a massive amount of users and network effects to actually be sustainable, right? And that's something we obviously want to avoid. But there is a solution. For some of these Tyco forks, we've been looking at doing slower block time. So Tyco now has a block time of 33 seconds instead of 12 seconds, which is, of course, Ethereum block time. That has allowed their cost to come down by about a third, which is good for them. But it's also really bad for users. You get a worse user experience. So the way we can patch over this is with preconfirmations. Just throw some preconfs on top. The downside of that is that without doing your preconfirmation designs in a clever way, you're going to end up with limited benefits. So your users are going to get very limited availability of preconfirmations, and of course, limited composability. So unless you're using a shared preconfirmation protocol, you're not going to have composability. So we start breaking a lot of things when we add preconfirmations. The other thing that specifically Tyco's case, you lose composability with layer 1 because preconfirmations happen over a course of an entire epoch perhaps, and during that time layer 1 state could change a ton. And so the kind of current layer 1 proposer is very different than who's actually sequencing the rollup. That's not shared sequencing, that's not based. But we can do better. Traditional designs are not good enough. We have, over the past 2 years, we have new research, we have new teams, we have a lot more data about base rollups because we have one live, and we have a lot better technology. So one of the big things that we'll be talking about in the next section is ZK, using snarks to save costs and improve efficiency. So let's kind of take a step back. Let's think from first principles with all the data, with all the research, and with all the teams that we have now, kind of what are the things that we really want to get out of base sequencing? The first thing is, in my mind, the most important, which is synchronous atomic composability. And this is a buzzword for sure. What I think that means is atomic cross-chain contract calls that are sufficient enough for flash loans. And the reason for that is because flash loans are a foundational tool for doing atomic arbitrage between domains. So once you have cross-chain contract calls, you can do arbitrage. You can do flash loans for arbitrage. And this gives you the ability to essentially arbitrage prices on different domains, giving users kind of the best prices across chains. You can also use that for doing like a swap that uses multiple chains liquidity. If I'm on Arbitrum, I could directly use Ethereum layer 1 liquidity without waiting for like a service provider or some collateral. Now, that's pretty straightforward. The other thing to look at is a seamless user experience and developer experience. So anyone who's ever tried making an asynchronous application will know that it's 10 times easier, I'm not joking, to build a synchronous application. If it's asynchronous, you have to deal with a case where something goes wrong and you have a desync. Now, the other thing is, of course, network effects, right? Once we have the efficient synchronous composability between chains, we have the ability to build network effects on one chain and use that on another. And because Ethereum already has massive network effects, that means base rollups can use those network effects, those liquidity users, protocols, etc., to directly improve the user and developer experience on their rollup. Now, the other thing that we want, of course, all the time is faster things and cheaper things. So on the faster side, we're looking at good preconfirmations that don't break things and that are fulfilled 100% of the time. Frequent block proposing. The more we touch Ethereum, the more we can compose with Ethereum. Custom front ends. So this is kind of changing the Uniswap style swap interface to something that actually represents what a preconfirmation might look like. So that's a green check mark, some confetti of some sort. It doesn't seem like a lot technically, but it's actually really important to improving the user experience materially. One thing is like getting rid of improvals and then swaps. We can get rid of that completely with preconfirmations. Another thing is, of course, cheaper things, which is better execution. So just writing your smart contracts better and not making kind of the mistakes that we've made in the past when we were rushing to get code out. Aggregate everything. There's a slide on that, so I'll wait. And of course, efficiency of all shapes and sizes. Now, we want to do all of these things, and both of these things, I guess, without sacrificing decentralization and censorship resistance, liveness, and sustainability. So this is where you can get faster and cheaper if you go to all layer 1. You can do it on a centralized sequencer layer 2. What you can't do is faster and cheaper with decentralization, censorship resistance, liveness, and sustainability without some form of base sequencing is my opinion. So we know what we want. It's not that complicated. We want fast things, we want cheap things, and we want everything to feel like one chain for developers and for users. Getting there. Next generation base sequencing. This is the subject of these 3 companies up here. This is kind of the industry that we're in. This is Rise, Spire Labs, and Tycho Gwyneth. And we're taking a very practical approach to unifying Ethereum. So we're trying to avoid the kind of discussions where we get into the ivory tower semantics and actually build like tangible, useful products that are good for users and developers. So let's get into the specifics. This is a intermediate talk, so we're going to get a little bit technical here. We're going to share literally everything. So when it comes to things we share, like if the answer is no, then you're probably lying. We have deposits, proposing blobs, proving network effects, assets, contract calls, off-chain infra, security, economies of scale, et cetera, et cetera, et cetera. So shared deposits, that's ag layer. These are teams that are working to reduce cost of posting ZK proofs to mainnet by aggregating ZK proofs. It also has the excellent benefit that you can do interop between layer 2s without ever touching layer 1, so you save a lot of costs with that as well. Shared proposing saves a lot of costs and enables atomic composability, again, between base rollups. If we can share blobs, so if you're a base rollup and you're frequently checkpointing or posting to Ethereum, you're going to be purchasing a blob for DA in most cases. And blobs are pretty big, and most base rollups do not use 100% of the blob space in a single blob. So there's a lot of empty space. And there's a whole bunch of teams. Spire is kind of leading some of the research on this side to figure out how we can have multiple rollups use the same blob. So we build some crypto economic system to make everything a little more efficient and a lot cheaper for base rollups. We also look at things like shared proving to save costs, shared network effects, so using the layer 1 for network effects instead of the layer 2s. And we kind of logically centralize our network effects for a better user and developer experience. And also, of course, shared assets. So we want the canonical ledger of last resort for every asset to be on layer 1. We want fungibility between these rollups. That's something that we get with shared deposits, but it's a big priority in of itself. Contract calls, of course. So we want to do contract calls. We want to batch those. Off-chain infra, that's pretty obvious. Security, that makes sense. And then, of course, economies of scale in everything we do. So one of these kind of tools is preconfirmations. We have over here in number 1, we have a centralized sequencer that gives out preconfirmations. This is what every layer 2 does today, except for Tycho. And number 2, we have some proposed models for based preconfirmations, where the layer 1 proposer, the guy running on a Raspberry Pi with a dial-up, is the sequencer, and they're the one directly giving out preconfirmations and directly interacting with the people who are requesting preconfirmations. So obviously a pretty huge bandwidth and compute resources cost. And number 3 is the design being explored today, which is some form of delegation, that's that purple line, to a gateway who actually gives out preconfirmations to users, and then they create some builder constraints, some set of rules that builders must build blocks that comply to, right? So the gateway is acting somewhat like a relay in this case, but with a little bit more constraint around the builders. So we still have an auction taking place, very similar to MapBoost. And of course, the builder gives the block to our Ethereum proposer, who goes and gives that out to layer 1. Now, the other thing that we want to do is MEV retention, censorship resistance, being included here, and of course, doing this all with preconfs, which turns out to be a really difficult problem. But we have some excellent research from the Ethereum layer 1 about execution tickets. So we've kind of extended this to layer 2 on base rollups. We have these things that look very similar to execution tickets. We distribute these in an auction, and then you must burn a ticket to propose a layer 2 block. Although we do some of the burning and kind of registration early in the epoch and off-chain optimistically, so that there's not an expensive thing to do on-chain. And of course, with this, we can throw in some no delay forced inclusion. So every rollup today has a drift where you can make a deposit transaction on layer 1, and then you might wait a few layer 1 blocks before that's included in layer 2. In a base rollups case, you can pretty straightforwardly build no delay forced inclusion right into a base rollup, which gives you, excellent censorship resistance equivalent to that of Ethereum. Now, one other important thing about next generation base rollups is checkpointing. So whenever Tycho calls this proposing, by the way, but whenever we want to kind of put our sequence onto layer 1, we need to make a checkpoint here. And this is a little red flag on my diagrams, but what we're actually doing is making kind of a point of atomicity, right? A layer 1 EVM transaction is atomic. You can't revert part of it. And because of this, you can do cross-chain contract calls based on that atomicity. You can also checkpoint together. That's this bottom left diagram where we share lots of checkpoints in one, which saves a ton of costs. The other thing we can do, of course, is other things while we checkpoint. So we can use layer 1 liquidity during our checkpoint, make this available on layer 2s. We can also save the states of things on layer 1. We could change the state of a layer 1 contract to simulate layer 1 execution, but actually doing the execution on layer 2. Cool. So one important kind of piece of technology, and probably the most important for the base rollup teams to compete on and be the first to, is validity proving and fast validity proving and shared deposits. So there's a whole bunch of ZK teams working on this. Succinct and Risio are two examples. And the goal is to take fast validity proofs for a whole bunch of layer 2s, combine these, aggregate these into one fast ZK proof, and then put this onto Ethereum in a shared deposits bridge contract that has funds for lots and lots of rollups. Now this has security kind of concerns. You have to trust your ZK, so we probably want multi-proving, and it's also today really slow. So the biggest competitive advantage of base rollups in the future will be how fast is your proving. Cool, so this is kind of the magic of base sequencing that we've been working on at Spire to some extent, of course. And that is using a censorship resistance committee to sacrifice liveness for censorship resistance. You can read more about this in our light paper. And then forward base sequencing, which is using a sequence posted in a layer 1 slot to affect a future layer 1 sequence. This enables you to do based sequencing and traditional shared sequencing at the same time, which is obviously super powerful. So if anyone from Espresso is in the room, take a look at this. Cool, so after we've done all this, what do we get? Harmony. And more specifically, deconstructing economies of scale to enable parallel innovation while maintaining network effects. I've said this in all of my talks so far this week, and it's so important, right? We don't want economies of scale to introduce centralization risks, and we want to promote parallel innovation as much as possible. The other thing, one of our important goals for the user and developer side is a monolithic experience, right? Nothing monolithic in practice, but we want to have the ability for users and developers to feel like they're on one chain, just to get that clearly better user experience. And of course, doing all of this while establishing infinite expressivity, giving builders the direct ability to customize whatever they want about the rollup, including execution environments, gas fees, etc. Infinite gardens, break walls. Next generation base rollups actually solve problems. Stay based. Oh, here's a quote from Heraclitus Drake. Stay based for one man's liquidity is another man's liquidity. Thank you.
Okay, thank you a lot. So we have a few questions. Yeah. So if you do play.
Cool. So first question, what can Tycho do to become a next generation based rollup? Well, first of all, upgrade their bridge contract so it can share proposals and deposits and ZK proofs with other rollups, and then add actually good preconfirmations. Yeah, they have a lot to do.
Okay.
Cool. Yeah, second question. As someone new to the space, I find it hard to factor out the marketing. How does your approach compare to Espresso? Sounds similar, at least. That's a good question. So Espresso is building a shared sequencer, and they're building a form of what they call based espresso, which is not actually base sequencing. But Tycho is building a They just call it that. It's a marketing thing. And the goal of Espresso is to unify layer 2s. The goal of next generation base rollups is to unify Ethereum and layer 2s. So we're involving Ethereum in the equation. But to get there, you can do shared sequencing. You can even involve the layer 1 sequencer. But that doesn't mean anything unless you do this checkpointing, unless you do this atomic synchronous composability. So base Espresso will not allow you to do cross-chain contract calls.
Okay, thank you. Do you have any other questions? We still have time. Okay.
Sorry, haven't figured out to log into that thing. So you mentioned that there is a no delay force inclusion. I'm kind of curious how that works with a chain reorg, where the chain state kind of change after, like if you force like a deposit, for example, and a chain state changes with a reorg.
Right. So this is something that every base rollup must do, which is reorg with Ethereum. So in the case of an Ethereum reorg, then your base rollup must always reorg. It doesn't have to change anything, but it will reorg. And this is something that is very hard to fix in protocol. So we need an Ethereum upgrade to reduce the risk of reorg or decrease time to finality. But there are a lot of outer protocol things we can do. So if you get lots of proposers opted in the look ahead, you can just ask them not to reorg, have them put up some collateral, and you'll be able to reduce the risk of reorgs. And you can also like paste over it on the user experience side. You can have a solver or somebody take a duration risk. The user never has to experience a reorg. And then Spire is also working on like an RPC that's custom, kind of retrofit to deal with commonly common reorgs. One thing I would add is that base rollups will reorg as much as Ethereum does now. So I don't know how much you use Ethereum, but if you do a lot of DeFi or trading, you still probably never experienced a reorg that has affected your life. So I wouldn't expect that it's a massive user experience problem. Yeah, right. We would have to reorg.
Okay, thanks. And then, sorry, just another question. I thought cross-chain contract calls was very interesting, but I still can't imagine how it works, like, across, let's say, like a bunch of different chains that all operates at a different speed, right? So could you maybe provide like some practical examples with like a bit more details?
Yeah, come talk to me afterwards because that's a longer discussion. So all base rollups have a batching time of 12 seconds and a block time of theoretically less, right? And this means that the kind of composability you do between them can only happen at batching time because that's the only time when you have atomicity and synchronicity, right? And so we can compose every 12 seconds, so we can do a cross-chain contract call every 12 seconds. And then within that kind of boundary, we can't do any composability that is enforced by cryptography, right? We could still do like intents or other kinds of interop.
Okay, thank you. Please give a round of applause to our speaker.